Hello, welcome back to Mini Rust in Rust. We're coding a little mini programming language that looks like Rust. We're coding it in Rust. Maybe that'll get confusing. So far, it's just been pure fun, apart from maybe one video recently that was a bit boring. This is video 23. Did I say that? And I wasn't going to record another one today. I recorded the others yesterday, and it's been playing on my mind that I left a situation that I'm not comfortable with, which is that we have a thing called a syntax tree, and we have a thing called a typed syntax tree, and they're really similar. It's just that the typed syntax tree has a type in every thing, and all this other stuff, leaf operation, assignment statement, it's all going to be the same between the two of them. And it's just playing on my mind because we're going to add more stuff. Like everything that you can do in the language is going to go in here. And we're going to just blow up how much we're repeating. So I did actually mention on stream last time that, or the time before, that there was a pattern we could follow that would allow us to share this code, I think. And I didn't like the sound of it at the time. But I thought about it a bit more, and I think it's probably okay. So we're going to give it a go. We're not going to need to add any tests. We're just refactoring a bit of code here. If it goes well, it'll be quick. So, well, we'll see how it goes. All right. So we have a thing called a syntax tree. We still want a thing called a syntax tree, and it's still going to contain all this information. And we have a thing called a type syntax tree. And again, we still want a thing called a type syntax tree. Still want it to contain this information, which is a type and essentially all the same stuff as a syntax tree. And I think the way to do this is to have a new thing called a syntax tree, which is probably going to be a struct type. And all it's going to do is contain, it's just going to be, I think it's just going to be a struct type like this that just has one thing in it. And it's going to contain something which I think maybe we'll call syntax node, which is the thing below. And a syntax node has a generic parameter of like what type of thing do you hold inside you. I need a semicolon there. And so this thing is going to become a syntax node, and it's going to take a type, and that's the type that's going to be in here. So I'll try and explain it a bit more when we get there. Yeah, so a syntax tree is just a syntax node, and a syntax node is something that can be either a leaf, an operation, an assignment, or a statement. But if it is one of these more complicated things, like an operation or an assignment or a statement, it's going to contain something like, basically, because a syntax node is like a recursive data structure. Previously, a syntax tree contained a syntax tree, and so so for example, an operation consists of some other expression on the left-hand side and some other expression on the right-hand side with, say, a plus, combining them together. So left and right were both of type syntax tree, but you can't have that. You have to have a box of syntax trees so that we don't have a recursive data structure. The compiler doesn't know how big to make it because it goes on forever with syntax tree inside a syntax tree inside a syntax tree. When we use box, it adds that level of indirection. That means it's a pointer to a syntax tree, so it knows what size a pointer is, so it's all fine. That was all waffle, but by saying we have this thing called a syntax node, which doesn't tell you what type of thing is being held in this box, could be a syntax tree, and later we'll see it could be a typed syntax tree. I think we'll be able to reuse this syntax node thing for both types of syntax tree, hopefully. So we've got some errors because some people are using syntax tree in a way that is not allowed. So the first thing is we're trying to create a syntax tree of type statement. And I think what I want to do, I could say syntax tree brackets syntax node of syntax tree : statement blah blah blah, but I think what I want is to add a function, associated function on syntax tree, which can make a statement for us. So if I make this lowercase, that means it's a function at least by convention, and it's going to take in the same as we were providing before. So now we need to make an associated function inside SyntaxTree, and it's going to return, it's going to make a syntax tree based on this box of syntax tree that we've given it. So it's just going to be a self. So I guess we could say this takes in it's going to take in a box of self. It's going to return a self, and the self it's going to return is going to be, it's a syntax tree because that's what self is. It's going to be a syntax node of type statement containing the expression. I think that's going to work, right? Because statement is just, statement just takes in a box of t, so that's all fine. So that looks like that has worked for that case, I think. We'll go back there and check it looks. Oh, I can't. I've lost all my errors. I don't know why this happens to me sometimes with Rust Analyzer or with COC. Alright, so here's another case where we're making a assignment statement, and again I'm going to turn this into a function, associated function called assignment, which is just going to take in the arguments that are needed to make an assignment. Oh, I lost a bracket. And now we need this assignment function to exist. So an assignment is created from a symbol token and a box of self and an optional symbol token. It returns a self. So far we haven't got any benefit for this, but by using this syntax node here, I'm hoping we're also going to be able to use a syntax node in the typed syntax tree, and we will start getting a benefit. So far we've just had to write a load of boilerplate which makes a syntax tree for you by calling a function, just basically just to wrap up all of this stuff. Otherwise we'd have to say syntax node brackets blah 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 blah. Or maybe not, because this, it's kind of, we wouldn't need the diagonal brackets because the assignment thing has got mentions t, and since we're passing in an expression here, it figures out what t is. So it figures out that this is a syntax node of type syntax tree. Right, this is like what it really mean. But we don't need to say that because expression already lets it figure out what t is. So we're all good. Okay, now something else that needs a similar thing. We need a leaf. And in this case, we can make another function that does this for us. In this case, I think we are probably going to have to say what type we are doing, I think. So it's going to be a self with a syntax node leaf containing the leaf token. And is it going to complain? No, it knows. Here it just knows because the return type itself, which is a syntax tree, what is the type of self? It's a syntax tree, which is, it knows that self is a syntax tree which contains a syntax node. It's just by definition that's what a syntax tree is. Because syntax tree contains this definite type that's been provided to syntax node. So even in this case where we didn't have a parameter that had that type in it, the return type is enough for it to know what type of syntax node we're talking about here. I don't know if I'm obsessing about why we don't need to provide that type here. Alright, we can call that same function again this time. So the last one we haven't dealt with yet is operation, I think. So we'll pass in the arguments needed for operator left and right. And we'll call the leaf function again here. And that operation function doesn't exist yet, so let's make it. Now let's get these things in the same order as they are in the definition. So it's leaf operation assignment statement. leaf operation, assignment, statement. Are they in alphabetical order? No. They're just in order of like complexity, I guess, or something. So maybe we'll change that order sometime, but for now, let's be consistent. So again, operation takes in an operator. A left, a right, and it returns a self. So why is leaf right? Why is this called leaf right? This should be called right. We should check the other argument names. Leaf token seems okay. Could be just called token this. It has no name here. We'll leave it called leaf token for now. So symbol, expression, declared type is all fine. Expr is fine here as well, I guess. I guess we should rename this to expression, shouldn't we? Why use an abbreviation when you can just use a real word? And here, left and right are actually left and right expressions, but we won't use that full thing. And we'll return a self, which contains a syntax tree, a syntax node of type SyntaxTree with an operation. And we've named our variables carefully, so that's all going to work. Now, who else is moaning at us? Right, so other places where we make syntax trees, we need to call these helper methods, helper functions now. It should be fine. In this case, this is a function when it used to be struct creation literal syntax. So these are now arguments we're passing in. And this is calling that construction function again. And same thing again. Oops. It's an operation consisting of an operator and two leaves. And these are arguments being passed in, so we can't have the nicer looking syntax where we say what each thing is. On the other hand, uses fewer lines. All right, same again for this assignment. So a little bit of, a little bit of pain here, but I think nothing is feeling too out of control right now. We're just going through fixing compiler errors that we know how to fix, so I think we're not too bothered. Alright, now we're going to make a statement. And in there is an assignment, and again, assignment needs, done it again. There's something I'm doing wrong that is getting me confused. So again, no names on these arguments because they're now arguments. And again, we call the leaf construction function. And now we do just an operation. And again, we call a little function to create leaf. And get rid of the names here. So just instead of using a struct literal syntax, we're calling a construction function. That's really easy when it already used brown brackets, and it's a little bit harder when it used curly brackets. But not too hard. Just every time we make a syntax tree, we make it using one of our new construction functions. That looks like that might be it. So let's see whether our test's passed. Shouldn't be anything different. Oh, we've still got a few compile errors. Other places where we create syntax trees, I guess. No, this is where we... Oh, hold on. This is not where we're creating them. This is where we're matching on them. So I guess we need to do some kind of cleverer matching. Like this. Does that work? Okay, I think it would work if this weren't private. So if we say this, then it might work. We're saying yes, you're allowed to kind of see inside what a syntax tree is and deconstruct it like this. The other option would be I guess the other option would be, do we need this? Will we still need this to be public? Let's see. Yeah, the other option is look inside tree to get the, yeah, it still needs to be public. I actually think it's still a better option though. It's just less complicated looking. So tree.0 just means get the thing out of syntax tree that's inside it. There's only one thing inside a syntax tree, which is this syntax node thing. So now we just match on that syntax node. But now, oh no, it's just not been imported. So we'll import it. Looks happy. Okay. So let's see whether we get away with just changing these trees to nodes here. We know the type of this thing is not just a syntax node, but a syntax node of syntax tree. So everything should type check fine. And it looks like that's working okay. Let's keep looking. Here we are creating a statement. So I think we can just call the construction functions we created. Oh, these functions need to be public. So we're using them elsewhere. So let's make them public. What other errors have we got? None. All right, so is now our test going to pass? We've got a warning. No. We've got an error in type check. Oh, so I've got the problem again that my errors are not showing up. Okay. So more construction of syntax trees. I was saying didn't enjoy these constructing these things in order to use them in tests, wasn't I? We construct an assignment. Oh, we've got to get rid of the same thing we were doing earlier. Get rid of the names here because these are just arguments to a function now. Any other errors? Is that really the last one? Looks good. Okay, our tests still pass. So we must have done a valid refactoring. And I will do a commit, but not quite yet because this doesn't actually do anything. I mean, I could do a commit now, but I won't waste your time with it. So what we haven't done is done anything to TypedSyntaxTree. So we're going to do something very similar to TypedSyntaxTree. We're still going to have a thing called TypedSyntaxTree. It's going to be a struct. And it's slightly different because it doesn't just have a syntax node inside it. It has a type, like all those things below have. And it has, I guess we're going to call it a node, which is a syntax node of which contains inside it typed syntax trees. So we're reusing syntax node in two places. We'll get rid of this thing completely now because it's all exactly the same except that they all have that type thing inside them. And I guess I wanted to change what this is called, but we'll do that later. Yeah, so we're reusing syntax node and we're saying the thing that lives inside you, if you have a thing inside you or multiple things inside you, is a typed syntax tree. And I thought, when I mentioned this previously, I thought it was going to be overcomplicated, but the repetition of code for no good reason makes it worth the complexity of having this thing called a syntax node, which is probably not as bad as I thought it was anyway. Or then maybe it could do with some documentation. All right, so everywhere where we create a type syntax tree, we've got exactly the same problem we had with SyntaxTree, which is that you can no longer construct it that way. Now we've added a function to, and this should probably be at the top, called assignment. And I probably want to delete, let's delete this type function while we're here, because we can just explicitly access that type field. And we probably want to make these things public, like so. Anyway, the assignment function creates a self, and it takes in some arguments. It takes in a type, and some other stuff which we'll figure out in a second, and it returns a self, which is a type syntax tree which contains a syntax node of type assignment. And here's where we figure out what the other arguments we need, because they're going to be these symbol expression declared type, that just guessed the type, which is quite nice. If it's right, that was really cool. It was almost AI-like. Oh, and this is wrong. This should, a self, of course, is not a tuple type like it was before. It has a node and a type. By the way, we need to call it type underscore because the word type is a keyword. Something like that. Now, expression. It shouldn't be a box of syntax tree. It should be a box of type syntax tree. So I guess that should be a box of self, we can say here. And I'm sure this code will get formatted in a second when our code is less completely broken. So when we're calling a function, we don't use these named arguments. That's only for type construction. It got laid out nicely now, so that's good. So how much more construction have we got? Well, here's a statement that we're building. Did it again. And again, it needs us to pass in a type and a thing that we're calling statement. So let's make this function exist. Put it at the top, since these things, but as constructors, they sort of belong at the top in my head. It returns a self, takes in a boxed self. This should be called type. And we're making a type syntax tree, which has inside it a syntax node of type statement, which, hold on, but self doesn't work like that. I'm just forgetting it again. Self has a type, and it has a node, which is this thing. And that's the end of self. Okay, so we've got an assignment and a statement. Now there must be other things like leaf. Oh yeah, well, this is no longer a function. We'll just refer to the type directly. Here we're creating an operation. So again, we'll make a little construction function for creating an operation. Generate that. These haven't generated as nicely as the ones generated before. Not sure why. But it returns a self, and it takes in a left and a right, which we'll just call left and right, and a type, and it returns. This time I'm going to remember that self is a struct-like thing with a type and a node, and the node is going to be a syntax node of type operation with the arguments we passed in, which hopefully already have the right types. And there's definitely going to be leaf that needs doing as well, right? Now, we've got a problem here that, oh right, yeah, we borrowed something from it. So let's just not do this anymore. Let's just do left typed dot type underscore right typed dot type underscore directly here, and not keep hold of references later. And again, we're referring to them again here. So this is why I did this, because it's a bit clunky. But it kind of makes it clear that we're not reusing this outside of here. Now we're not calling it a function anymore. It seems all right, I guess. There's a lot of typing I've had to do for this. I'm starting to realize why I did it. I think it's okay. These lookups, I think, will get compiled away at compile time, and they won't actually result in any inefficiency, hopefully. Now, what's it complaining about? Oh, it's still complaining that left typed has had stuff borrowed from it. All right, undo all of that because it was too much typing, and instead we'll just clone these types. I briefly made them copy in last video or the one before, so we wouldn't have to explicitly clone them. And then I started thinking that maybe types are going to have more complicated stuff inside them at some point. Maybe I should have Yagni'd it, but yeah, making things not copy is probably safer. The safe way round to approach these things. So when we're making a leaf, we're going to pass in a type and a token. And we need to make this constructor function. And leaf definitely goes at the top. We'll figure out the order in a minute and make sure we've done it right. But definitely leaf is first. This returns a self. And how to make a self is we have a type and a node, which is going to be a syntax node of type leaf, taking in the token, which for some reason here is called token, not leaf token. We should make our mind up about what it's called. Let's just call it leaf token for consistency with what we did in SyntaxTree. Okay, expression.type there, not calling a function anymore. I guess we need to clone it to avoid that problem. And then here we're matching on the node. So it's going to be, instead of type syntax tree now, it's just going to be syntax node. Like so. Now, leaf has, oh no, yeah, and we can go back to leaf not being a structured type, like a thing, but a thing. All right, and this should be looking at taking a reference to that. Yeah, see, leaf on syntax node only has one property inside it, so we didn't give that property a name. It's kind of inconsistent. I kind of wish we'd done it differently, but we still could change that later, but we won't do it as part of this change. We'll do things one at a time and probably won't make that change because it's probably fine. So again, we're matching here on the node that is inside a type syntax tree now. And this is going to be syntax node. Let's do that again. Syntax node. Like this. And leaf only has one property, as we were just saying. And this time we want the type. Oh, hold on. So yeah, I guess we want match self.type. And any operation we match self.type, and then we figure out what to write about it here. And we should take a reference here. So I think we're still, nothing feels like it's going to break. Just little bits and bobs that have changed because it's changed. So much nicer to be doing this stuff in Rust than in many other languages where we've got proper type checking that has our back. All right, here we're constructing an assignment. So these are just arguments, just like before. Here we're constructing a leaf. Passing in a type and a token. Looks all good. Similar here, we're constructing a statement. And inside that we are constructing an assignment. So these are just arguments. And here we're constructing a leaf. It does slightly hurt readability when you call a function instead of construction syntax, because now these arguments are not named anymore. But I can't immediately think of anything we could do to make that better that won't undo the exact thing we're fixing. All right, a few more errors left. Here we're making an operation. I haven't forgotten yet that we need to reorder the construction functions inside our typed syntax tree. I think type should come first, right? Operation takes a type as the first argument. That was a little odd that we've done that at the end, but we've been called out on that because the order of arguments matters, whereas the order of things in like struct construction syntax can be anything. So again, the types come first, but also you can't use named arguments. Not that. So these need fixing because we're just calling the leaf function. Takes a type and a token, and we've got no errors in this file. And that looks like those errors don't exist anymore. No, hold on, they definitely do exist. This is not valid at all. All right, so what are we doing here? We're in the evaluator. We've been given a type syntax tree, and we're looking for the node inside it. And I think we can just replace these and see what happens. Of course, if we need the type information anywhere, then we're going to need a bit more. Matching on leaf looks like this now. And same matching on statement looks like this. Any more errors? Nothing so far. How are our tests doing? Great. All right. So we did say we were going to just change the order of the construction functions. Well, that's not. I thought I was jumping to a construction function. So wasn't. Let's go back to where we are. So here we are calling a construction function. So it's going to go, how does syntax node look? It goes leaf operation assignment statement. So leaf operation assignment statement. We'll get rid of the thing we commented out, which was this type function. That was needed because everything inside a type syntax tree had this type, had its own type field, and we needed them all to come out. So instead of that, we can just look directly for that type field in a type syntax tree, and we do have to clone it quite a bit. As long as that still all passes, I think we're happy. So just to kind of recap what we did, this diff's not going to help us recap very easily, is it? I will make this commit at the end of this stream or after this stream. Before that, I will check through the diff, but before we do that, let's just recap in the code what we did. So what we did was, previously we had a thing called a syntax tree, which looked like the thing which is now called a syntax node. And whenever we were recursively referring to something like an operation that itself has syntax trees inside it, we had a box of syntax tree. But now, in order to reuse syntax node in two places, we, instead of saying you always have a syntax tree in here, we say you have a T in here. You can say what the type is of that thing. And there's two things that make use of syntax node, and both of them like explicitly say exactly what type the syntax node holds onto. One is syntax tree, which always contains a syntax node of syntax tree. And the other is a typed syntax tree, which always contains a syntax node of typed syntax tree. So in both cases, these syntax trees are kind of recursive data structures where a syntax tree itself might contain other syntax trees. And now they're doing it via this level of indirection, this thing called a syntax node. And you might say, if you're from the C++ world, that this syntax node is following a pattern called the curiously recurring template something pattern, which is about basically you get given in your type definition the type of the thing that you contain, which is a bit odd if you look at it that way. But if you look at it the way we did, it's just that syntax node has like reusable. Oh no, I guess that the curiously recurring pattern is you're given the type that you extend or inherit from. That's why it's curiously recurring, I think. So in this case, this is just as generic. This is a generic thing called syntax node, which can contain something of type T, which we tell it at compile time. So nothing should have got any slower or anything like that by what we did. But what we have managed to do is share this code inside syntax node so that when we add more things, more types of expression that we can deal with in our language, they only go here. So we've simplified our life, hopefully. All right, let's have a quick look at that diff. And just double check that it is only doing stuff to do with the change we just made. No, it isn't, because there's some fixes. This stuff is some fixes from the previous video. So I will unpick that. Or I'll just do a horrific commit with both bits in after the video. So just, yeah. Oh gosh, this is no use to you. All right, so believe me, well, that's the only change we made today. We made this nice syntax node thing which shares, which like reflects the structure of both types of syntax tree that we have. Hope you enjoyed. Next time we will genuinely get onto kind of fleshing out this to be more like a language you could actually use for something, hopefully. See you then.